guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So since we went over electron configurations, now it's time to talk about periodicity of atomic properties. And this is also known as trends in the periodic table. And these are specific patterns that are present that illustrate different aspects of a certain element, including its size, as well as its electronic properties. So major periodic trends include electronegativity, ionization energy, electron affinity, and atomic radius. And so they group different elements into little families in order to better understand them. So I'm going to start out by talking about atomic radius. And so this is 1/2 the distance between the nuclei of two atoms. But then when we talk about two atoms that are nonmetals joined by a covalent bond, this is called a covalent radius. We also have an ionic radius when two ions are joined by an ionic bond. So this is when we don't have mere atoms. So if you look at this periodic table, we can see that atomic radii increase down a group, as you can see with this red arrow, and atomic radii decrease across a period. So basically, it increases to the left. So the reason why it increases down a group is because we have additional shells further from the nucleus. So for example, let's compare lithium that has 3 electrons. If I draw out the electronic configuration in this Lewis structure, I have 2 shells with 1 electron in the outer shell. But then let's draw sodium. Now sodium has 11 electrons, so we have 1, 2, and 3. And let me draw in all the electrons. So as you can see, there's 1 whole extra shell, and that's why the atomic size increases down a group. So the reason why the radius decreases going this way across a period is because electrons are added to the same shell and increasing nuclear charge draws them in. And so comparing sodium versus aluminum, which is right here, let me just draw the 3 subshells like so. And let's just pretend I already drew the 10 inner core electrons, and then it has 3 in the outermost shell. So now since there's 2 extra electrons in the same shell, there's increasing nuclear charge, the protons in the center of the atom, that draws in the outer shell because the positive nucleus draws in the negative electrons, and thus the size starts to decrease. And so ionic radii that I talked about right here show the same trends. They increase down a group and decrease across a period. But cations, which are positively charged, are smaller than their parent atom. And anions, which are negatively charged, are always larger than their parent atom. So this also makes sense from what I talked about before. Imagine something that's positively charged. That means that it's lacking an electron. So it has 1 less electron. Think of it like the sodium right here. So it's smaller than the aluminum, right? In the case of anions, it says it's negative, meaning there's extra electrons, meaning that there's more electrons in the same shell, meaning that there's more pull from the positive nucleus. So another term that I wanted to introduce is isoelectronic. And so this is when atoms and ions have the same number of electrons. So an example of this is sodium plus, which sodium has 11 electrons usually, but plus means that it lost an electron, so it has 10 electrons. Another example is magnesium 2 plus. So magnesium usually has 12 electrons, but it lost 2 electrons, so it has 10 electrons. And finally, F minus. So fluorine usually has 9 electrons, but it gained an electron because of this negative charge, and it has 10 electrons. So we can say that these 3 ions are isoelectronic. And now we'll move on to talk about ionization energy trends.
The only one that ever reached me was the son of a preacher man. The only